Challenge day number 2, we're going to look at the 4 problems I gave you guys earlier in class. The first problem says figure shows triangle ABC is inscribed in circle D. When they say circle D, the D implies that that is the center of the circle. It says if the measure of angle CBD is 44 degrees, so I'm going to mark that here, CBD, 44 degrees, then find the measure of angle BAC. This thing's going to be all crazy on me. So down here, this is where X is located. It is the inscribed angle down here. Now, to get the inscribed angle, it'd be awesome if we knew how big this arc was. So we're going to have to work on how big this arc is up here. Now, the first thing I recognize is this is a special kind of triangle, BDC. It must be an isosceles triangle because BD and CD are both radii. Therefore, angle B and angle C are our congruent base angles. So angle BCD must be 44 degrees. And now we can figure out the vertex angle of the isosceles triangle by taking away our two 44-degree angles away from 180, and we're left with 92 degrees. Now, that 92-degree angle for the isosceles triangle is a central angle for the whole circle. And a central angle and its arc BC, are the same angle measure. But now we can take that 92-degree arc and go back to the inscribed angle and divide it by 2, and that angle must be 46 degrees.
Problem 2, we've got a circle and we got a bunch of segments going on here. We have a bunch of chords crisscrossing paths. We have all these various values here, and we're trying to figure out what are specifically X and Y. Well, in our chords, we can only really deal with 2 chords at a time. We have to find the chords that are intersecting paths with each other. So, like this chord and this chord, or we're going to be dealing with this chord is intersecting paths with this chord. Now, the other 2 chords really are not intersecting each other and splitting each other up into various lengths. So we can't deal with these 2 pieces. So again, we're going to have to do this set of chords, and they both intersect each other at this point right here. And so we're going to be able to use the formulas that we discussed. We're going to take the inside part of one chord, so that would be this 3, times the rest of that chord. But the rest of that chord is made up of 2 parts, the X and the 5, that we have to add together. So we're going to have to put this in a quantity. So 3 is one inside part, X plus 5 is the other inside part. And again, that belongs to one chord. And that is going to be proportional to the same thing of the other chord. So the other chord that crosses its path is the 6 with the Y. So the 6 represents one part, and the Y represents the other inside part. And so now I'm going to have to distribute the 3 to the X and the 5. So we get 3X plus 15 equals 6Y. But I can't solve for X and Y with just that one equation. So does that mean we need to erase this, start over from scratch? No. Let's hold on to this. So let's backtrack, at least in our picture here. We just did those 2 chords, but what if we had used this chord with this other chord? And then we get a similar looking problem. They both intersect paths here. And so let's set up the same type of problem. So let's look at one chord. And you might go, hey, can't we just take this same 3x plus 15? Not exactly, because now notice the x isn't with the 5, it's with the 3 on this side of the intersection point. So we've got the quantity 3 plus x, or x plus 3, times the other inside part on the other side of the point of intersection, the 5, and that's going to be equal to, and then we can look at the other chord, and it's going to be the 8 and then times the y. So nothing special there, just 8 times y. Now in this case we get to distribute the 5, and we'll get 15 plus 5x equals 8y. But again, I can't solve for x and y with just that one equation. But if you notice, if we had our original set up here and now our new equation here, we could have these work together. And we could solve this with substitution or elimination in a system of equations. So now let's bring all this together. So let's get rid of some of this in here and here, and let's shove those two equations together. And then see how we could solve for x and y. Nope, come on. Try this again. There we go. Let's clean all that off. Perfect. And now you should be not connected. Oh, no, don't want to rotate. Thank you. Still connected? Yeah, all still connected. All right, let's try this. Disconnect. Take you. There we go. Oh, left the 1 behind. Got to go back and grab the 1. 1, here you go. Join your 5. There you go. Okay. Now, in order to do substitution elimination, and I'm going to do this with elimination because it doesn't really look like a friendly substitution problem, though you could probably turn it into a substitution problem, but you're probably going to deal with a lot of fractions. I need to get my x's, y's, and constants all lined up. And notice this x is not lined up with the other x. This x is not lined up with that x. At least the y's are lined up there. So one of two things we could do is we could just switch the order of these so that the x is now over here and then it's underneath the 3x and this 15 matches over there under that 15. Or you could make it look like most stereotypical systems of equations. You could have the x term, then the y term, and then equals the constant. But honestly, it really doesn't matter if that's how it goes. So I'm just going to flip-flop these two terms here, okay? So I'm going to write the 5x first and then the 15 second. So 5x and then the plus 15. So again, my x terms are lined up, my constants are lined up, the equal signs are lined up, and the y's are lined up. So now I'm ready for elimination. Now, I could either try to eliminate the x's or the y's. In both cases, I'm going to have to multiply both equations by something to get the x's to match up or the y's to match up. So, I don't know, I'll focus on the x's. I'd have to multiply 3x by 5 and 5x by 3 so that these would be matching 15x's. Okay, so let's distribute the 5 all the way through and the 3 all the way through. So top equation will have 15x plus 75 equals 30y. And the bottom equation will have 15x plus 45 equals 24y. Now I've got my x's ready to be eliminated, but do I need to add or subtract these two equations to get the 15x's to eliminate? I need to subtract, and really keep in mind, I'm not just subtracting the x's, but I'll be subtracting everything in this second equation. So 15x minus 15x, gone, eliminated. 75 minus 45 leaves me with 30. Then my equal sign, and then 30y minus 24y's is 6y. Divide the 6 over, and y is equal to 5. Now, to figure out what x is, I get to plug y equals 5 into any equation I want to. And so I'm just going to come up here to this top equation that I originally had, and I'm going to plug 5 into the y, which means 3x plus 15 is equal to 6 times 5, 30. Subtract the 15 over to the 30, and I'll be left with 15. And divide the 3 over, and I get x is also 5. Now, you might look at this and go, but this and this piece don't look like they're the same length. True, they don't look like they're the same length, but mathematically, they are the same value. So, not drawn to scale. So there's problem 2.
Number 3, at first glance, this looks very menacing because there is zero information that is specifically given to you here. But some things to note is we've got a diameter here, and here's an inscribed angle, so it uses this whole semicircle. So number 1, this must be a 90-degree angle. The second thing I notice is there are 3 lengths marked as congruent. And obviously the radii are congruent, but for this extra piece to be congruent as well, is a little bit extra piece of information. If I can stop pressing random buttons here. So what I would consider doing is, what if I drew in another radius that's going to be congruent to these radii, and then I notice I've got an equilateral triangle. So all of these angles are 60 degrees. And I knew this whole big thing here was 90, which means this little sliver is 30. Now, jumping over to this triangle, it's an isosceles triangle because of our two radii, so the base angles are congruent. So this is 30, which is our x in question here. So that takes care of part one. And then where are we going to go from here? This is 60, 60. So this central angle is 120. I could use a straight angle postulate with that 60 right there. But angle y is on the outside of this, so we could use the outside angle formula. But we would need to know how many degrees this arc that is closer to it is, and the arc that is further away from it, all the way back to here. We can use the central angle of 120 to say that this arc is 120, which means how much is the rest of this whole thing? Is 240 to get a whole 360 for the circle. So y, the outside angle, is equal to half of the arc further away minus the arc that is closer. We're taking half of 120, which is 60. And 60 is y. And the last problem. AB is tangent to circle C. Again, whenever we're calling a circle by a letter here, we're talking about the center point. So it is tangent to circle C at point A. What is the exact length of BD? And BD we know is at least 8. We just got to figure out how much extra EB is. So I'm going to call EB my x here. And I notice I'm dealing with lengths, and these lengths are intersecting on the outside of the circle. So I'm going to be using the outside length formula, which was the outside times the whole of one secant times the outside times whole of the other secant. But the other secant in this case is a tangent. So the outside and the whole were the same thing. So really we can take 16 squared, which is 256. The outside of our one secant we called x, and the whole thing is x plus 8. So now distribute the x, and we get x squared plus 8x equals 256. We can try to factor this if we can. Do we know two numbers that multiply to be negative 256 and add to be 8? And I would tell you that the answer is unfortunately, once I check my paper here real quick, no, it does not. So I'm going to backtrack so that we can complete the square. Move this equal sign over just a smidge. And now this is an easier completing the square because we don't have to worry about dividing anything out here. So I'm going to take half my b term, which would be 4, and square it. We get 16. I'm going to add 16 over to the 256. Now this is x, and then half of that b term plus 4. So this is x plus 4 squared. 256 and 16 is 272. Square root both sides. We'll have x plus 4 equals plus or minus the square root of 272. And x will equal negative 4 plus or minus the square root of 272. Now, there is no way that x could be negative 4 minus the square root of 272. That would produce a negative result for the length of EB. So I know I can go ahead and erase off the minus of the plus and minus. So this length is negative 4 plus the square root of 272. I wanted to know the exact length of BD. So really, I'm going to take 8 plus negative 4 plus the square root of 272. I can add together the negative 4 and the 8. That would be 4 plus the square root of 272. And my last little thing of business here would be to simplify, if possible, the square root of 272. Now, let me see here. Calculator, 272 divided by 4. Hey, that works. Can 4 go into that? And it can. So if I can divide 4 twice, that meant I could divide 4 and another 4, which is really 16. So the square root of 272 is 16 times 17. And the square root of 16 is 4, and the square root of 17 is prime. So really, my final answer would be 4 plus, now this guy, 4 root 17. And I can't add together the 4 and the 4 because this 4 is attached by multiplication to the square root of 17. And there is the exact length of segment BD. That is all for your challenge problems, and good luck to you tomorrow as you take the quiz.